Okay, this is Simple Circuits 2. Simple Circuits 2, and we'll be looking in detail at the potential divider. Okay. Right. Now, let's start with our circuit. We've looked at something similar before, so we're going to start again with 12 volts. And this supply, we're going to assume there's no internal resistance, and we're going to connect this 12 volt supply to two resistors of different resistances. Let this resistance here be of 10 ohms, so this is the greater resistance, and then another resistor here of 2 ohms, so a small resistance like that. Now it's a simple series circuit, so the current I flowing from there returns back there. Now, reminding you again, where there is no resistance, there's no potential drop. So of course we will have a point there, would be 12 volts. And then here there's no potential drop here, so this is going to have to here be 0 volts there. So the total potential drop across the two resistance is 12 volts. Now I want to calculate the voltage, the potential drop across each resistance, and to compare them to see how much potential is dropped across each one. Now we'll stick to the method we used before, which is applying the equation V equals current times resistance. Now the first thing I'm going to do is I'm going to calculate the current going through it, and then once I've calculated the current, I will calculate the voltage across each one of here. I will call this one here V1 to there, and I'll call the potential drop across this resistance is equal to V2. Now of course V1 plus V2, if I've done my calculations correctly, they should add up to 12 volts. Okay, so I'll give myself a little more space, and I'll draw it again. So here we go. 12 volts supply, 10 ohms, 2 ohms, current going in, and across, so this is our 10 ohms, 2 ohms, and we have a voltmeter V1 across there and a voltmeter V2 across there. So applying V equals IR as before, we find that the current is equal to the total potential drop 12 divided by the total resistance, which is 2 plus 10, which is also 12. So that's 10 plus 2. So the current flowing through the circuit, at every point in the circuit, the current will be equal to 1 amp. Okay, I'll clear this to get myself some more space. So we have current equals 1 amp. Now I'm going to apply V equals IR to each of those resistances. So here, now going through there, so we have V1 will be equal to 1 amp, 1 multiplied by 10 ohms is equal to 10 volts. And V2 is equal to 1 amp times 2 ohms, which is equal to 2 volts. Now you can see from here that the greater the resistance, it would appear, the greater the potential drop. So 10 ohms gives you 10 volts, and 2 ohms gives you 2 volts. So the greater resistance, the greater the potential drop. And we can use that theory now to look at a potential divider. So here's our 12 volt supply, 12 volt EMF if you like. Now if we connect the whole of that across one resistor, we'll find the potential drop there's no potential drop through the wires, which assumes there's no resistance. We'll have a potential of 12 volts, again assuming no internal resistance at all, and here we'll have a potential of 0 volts. Now, what I'm going to do, connect to here a voltmeter, and like that, V, and to the voltmeter we will have a pointer. And I'm going to point the pointer just there. So it's right in the middle. Now we're assuming that the resistance is a sort of constant wire through it, so that further along you go you get a greater resistance. So here we have, it's halfway along that resistance. So that's 12 volts there, 0 volts there. Halfway along we're going to have potential drop of, in fact, 6 volts. So in this position here we will have V is equal to 6 volts, because the resistance is proportional on that wire, so when we split half it there, that's 6 volts. Now I shall put the pointer in another position. This time we will split the potential divider. We'll put the pointer a third of the way along there. That's about a third. Let's put the voltmeter here. This time it's a third of the way along there, so most of the resistance is there, and as V equals IR, we have the voltage is proportional to resistance, so therefore that's a third of it, and so therefore in this case here the voltage will be equal to 4 volts. Okay, now let's have a look here. What would happen if we put the pointer, the slide if you like, right at the end there? Now, what will be the potential drop now? Well, if that's 12 volts there and 12 volts there, it will also be a potential of 12 volts just there. There's no resistance for it to drop across, assuming no internal resistance and an infinite resistance in the voltmeter. We'll find that the voltage there, the potential drop, is in fact no potential drop at all. So in this case here, potential drop equals 0. And in our last example, this time we'll take the other extreme. What will happen if we have our voltmeter pointer connected all the way across, or this end here of the resistance? So we're taking the whole of the resistance here, and what we'll find here in the whole of the resistance is we'll find the potential that is 12 there, 0 there, so this time the potential drop across our potential divider here is 12 volts. Simple as that.